Um, if you haven't done the class feedback, please do so. It's posted on Piazza. That's for IACS specific. Final projects, you should know all the dates by now. So the videos are due into this week, right? 6th. And then next week, so we have one more lecture, which is Wednesday. That'll just be wrap up. And then next Monday and Wednesday, we'll see people's video presentations about we'll just sit and watch people's final projects presentations in class. Possibly get people to comment on them or something like that. Anyway, it's been pretty good in the past. Pretty interesting to see what people have done. And then the 10th, everything is due. So today I was going to talk about sort of some of the problems with parallelism. We've talked a lot about most of the things here. This is just sort of talking about them more specifically, and then ways to avoid them. Just sort of general practices and approaches at a high level to avoid them or to engineer around them to make them easier. So a lot of the problems come with cache, are cache associated, particularly in the multiprocessing world. You have n threads, so you're gonna have n, if you have 2 threads, you're gonna use twice as much cache, or have twice the working set, probably, or just the local access. But even worse, you have n squared sort of interactions, right? Every thread might have to deal with every other thread, depending on the problem you're doing and what sort of regime you fall in, whether it's embarrassingly parallel or some sort of work stealing or something like that. But those interactions also have to go through the cache, have to go through memory. That's really our only way, or our primary way for threads to communicate. So you have locks and other primitives that there's a lot of crosstalk, and if you have n threads trying to lock, you basically have n times n number of possible collisions. And you also have then the read writes to shared memory, so you're sharing a bus, you're dividing up whatever limited bandwidth you already had for transferring memory into the cache between the multiple threads. If they're dealing with different parts of different parts of memory and doing a lot of memory intensive work, as we've seen in some of the problems, you can't get very good performance because if you're memory bound, splitting the work across multiple threads doesn't give you any more bandwidth, and so you can't go faster usually. And we see that in we've seen that in some of the problems we worked on. We've seen that in some of the examples we've gone through. One really common way this shows up is cache thrashing. This can happen already in single-threaded applications where if you have a really bad, this is some of the examples that we ran through with looking at L1, L2, L3 behavior as you walk through an array or access memory. So n threads working together where you have a limited cache, right? And everything that doesn't go into anything that goes past the cache to memory or the next level of cache is much slower. You have to either be very careful about the way you use shared data. Either everyone works on the same piece of data or same area of you either have to say, okay, we're all going to work together on this small amount of work and this small amount of memory so that we can keep this in cache and hopefully not step on each other's toes as we modify the data in cache, which we'll talk about in a second. Or you basically have to divide up the working set, right? You're implicitly or explicitly, you're going to split up the cache and get 1 over n of this very limited resource already. So both of these are painful, right? You either have to re-engineer your algorithm to work in the same limited region of your, you've got some large problem to work on. You can fit some small part of it in cache. So you either have to concentrate all the compute on that small problem so that the cache stays fresh for all the threads, or you're basically going to divide up the cache into small pieces, effectively divide it into small pieces while they work all over the place, but then you get much less cache efficiency. Yes? Are there low-level commands to manipulate what's in the cache? They're limited ones. There's not really much. You can do prefetching, right? That's about the only one is prefetching, and then the rest of it's just behavior. If you access something, it goes into cache. Prefetching is, so you can, we didn't talk about it in this class. It's much more a sort of hardware architecture. It's basic, or not really architecture, but low-level programming. It's if you know that your algorithm is going to access another piece of memory, something you haven't been working with yet, soon, but you don't need it yet. You can put in a prefetch instruction that says, basically, I'm going to need this memory soon. Start the process of loading it in. So for example, if you're walking through linear signal, processing it, and you know you're going to be working on the next block soon, you can launch a prefetch, and hopefully by the time you get to that, get to the code that actually needs that memory, it's already there, in some level of the cache. But in general, you just have to make it's behavioral. The cache services requests on demand. And so to change your cache behavior, you have to just change what you demand and how you access things. So you're either going to, if you do the naive thing of just working independently, then basically you've divided your cache by your number of threads. Now, that may not be too much of a problem if you've got independent L1 caches, for example, on the multiple cores, and you've only got threads for each core. If you start to add more threads, or if your working set is large enough that it affects L2 or L3 or one of the shared caches, then this becomes much more of a problem. And so you'll see, this is where you see poor scaling, especially in memory-bound or somewhat memory-bound applications, where you add, at a certain level you add threads, it's not too much of a problem, it's not running up against the cache limits, and you see good performance increase, and then suddenly it just drops off or stops improving. And this is because at some point, one of the memory bottlenecks, cache bottlenecks, something, you have reached the limit, and you can't go any faster with your current strategy. You either have to figure out how to be more efficient at cache usage or bandwidth usage or whatever the shared resource is that you are choking on. And one thing that a lot of algorithms are optimized for serial performance, where they're going to use all the cache as much as possible, because everything they put in cache is efficient. And this is potentially the worst case for end processes, where you have every thread is basically trying to use as much of the cache as possible, or is running an algorithm that runs well if everything's in cache. But then you've got multiple threads loading new data into cache and ejecting data from other threads, and you basically get worse performance than if you just run serially. One example, so we talked about the cache oblivious algorithms. Not talking about just generally oblivious, but cache oblivious matrix multiply, right? Where we talked about the subdivision problem, right? Which a lot of the cache oblivious algorithms have. They subdivide down, the model being that reads from global memory are expensive and reads from cache are free. So you take something like this matrix multiply and you look at the upper left quadrant of C, and it can be computed from these subproducts of A and B. So you divide down, and eventually this will fit in the cache. Now, we never said which cache, right? We didn't say L1, L2, L3, we just said it fits in the cache. And the truth is that at some point in the subdivision, right, we keep subdividing, and we change the memory layout so that this block, for example, is all stored contiguously, and then each subblock is also stored contiguously, so they all behave well with the cache. And so at some point, some very small part of each matrix will fit in our L1 cache. And we just assumed that. We didn't say anything else about other caches. We didn't talk about the cache hierarchy when we were talking about cache oblivious algorithms, right? We talked about fits in the cache. But really what's happening is we have several caches, right? And they grow in size, and they slow down, right? The L1 is much faster than the L2, but it's also much smaller. Likewise for L2 and L3. And so as we're doing this matrix multiply, we have several times where we get a speed increase, right? We subdivide A, and at some point, part of A fits in the L3 cache, right? And so after that, all the operations here, they're not free, but they're not as expensive as going to global memory. And likewise for the L2 part and the L1 part. As we subdivide down, the different parts of the matrix will be in there, and then fetches to, when the green square shifts down here, it's not as expensive as loading data from global memory. And so we get benefits all the way down, right? And that makes it very easy, and it's very efficient, and it'll use cache basically almost perfectly in terms of the number of memory reads. It'll load up L3 and use that data many times before it ejects it, and then might read it once more, but far less often than the naive matrix multiply. Yep.
Are there tools to examine like a Python cache?
Sorry, are there tools to
Examine like how you're using cache, like you're hitting L1, L2, L3.
Are there tools for looking at cache behavior and hits? Yes. We didn't talk about it in this class because, partially, sadly, so many people are on Macs, including myself. The Mac tools, there's instruments. I think it's still called instruments, right? It keeps changing. There's a tool called instruments on Macs that tap into the Intel performance counters. You can also get them just with the perf command under Linux, not inside a VM. So we avoided these. If you're running on a Linux actual machine, there's the perf command, which gives you a bunch of, taps into the Intel performance counters or AMD's equivalent, which there are counters on the chip that say, I access memory, increment, if I had to go to global memory, increment this counter. If I had to go to L3, increment this counter, increment a miss on L1. And they'll give you reports. You run a program for some amount of time. It's free because these counters are always kept anyway. And it will report all of the counts for cache hits, misses, all the levels, and various other accesses as well. Under OS X, it's a little bit trickier. You basically just look for, Google for instruments and cache counts or cache performance counters. It's a little bit more involved to set up there. They are quite nice though, and if you're unclear why, if you're running something and you don't see performance increase and you wonder, which am I missing on cache, or is it going to disk, or is it some other thing like that, this is very effective. It was unfortunate that there's not a good unified standard because I would have liked to talk about them. So anyway, so the matrix multiply and other cache oblivious algorithms will use all of the levels of cache very effectively, right? It'll load up this data and use it a bunch of times before it moves. But if we try to do something just like, if we do the naive parallelization of this algorithm, right, we're gonna have some other thread working someplace else in the matrix. And it's gonna want L3 to be filled with this block, and L2 to be filled here and the L1 cache down here. So if we're sharing, we're probably not sharing L1, those are usually independent core to core. But if we're sharing L2, and the thread ends up down here with the other one up there, we're basically, every time I load something, I'm ejecting something useful for you. And likewise, each thread is, when it reads data, writes data, is poisoning the cache of the other process. And they're all gonna have to go to L3 or worse, they're gonna be non-overlapping memory, and L3 is gonna get blown out as well. And we're basically, every read and write is gonna go to global memory, right? Just with the naive, right, parallelize this operation, right? There are 4 sub-blocks of C. Seems like an obvious thing to just parallelize quickly. And in fact, if you parallelize, I'm gonna give advice later, which is parallelize outer loops rather than inner loops, like parallelize at the top of your algorithm. So the first thing you might do is subdivide C into 4 parts, compute those 4 parts, and then you've got basically worst case cache behavior because everyone is looking at different parts very far away, right? So it's very easy to take something that, a serial algorithm that's very performant, very effective, use it in a parallel process or use it in a multi-threaded process and drop your performance relative to what you could have done serially, right? Right. The whole idea of this was, of the cache oblivious algorithm, was use the memory bandwidth as efficiently as possible, right? Load everything once or a limited number of times. But if you've got these 2 processes arguing over what should be in cache, that's not going to happen. You could actually drop performance significantly just by adding another thread. All right. Another sort of cache-specific thing is false sharing. So suppose we've got two workers doing different things. One thread is going to repeatedly write to X. It's incrementing a count or updating, doing some sort of calculation that involves writing to memory. And another thread just repeatedly reads from some value or some set of values. It's going to, maybe it's writing some other value and then it goes and reads a variable, sums it up, reads it, for some reason. Right? This is great, all right? They're going to be doing separate things. They're working on separate memory. They're not going all over the place in memory. They're just mostly concentrating on these two values. Perfect, unless the two values are next to each other. Especially if they land in the same cache line in particular, right? Because then, every time X writes to the cache, or X writes to, right, one thread writes to X, they've got this cache. They've got some sort of cache coherency protocol that that Adi talked a little bit about, where you've got multiple processes. When one of them writes to a cache line, if some other process also has that memory cached in its local copy, that will get invalidated through some side channel. And when it goes to read the value, Y, it needs to go to memory again. This is very easy to do, unfortunately, especially if you've got a structure where you've laid out multiple values, right? One of them is, you're doing some processing and you do some operation on an object that involves writing to it, and another one that just involves reading from it repeatedly. Maybe once in a while X writes to Y as well, and so it has to keep reading to check for an update. Every time this happens, this is easy to do. Every time there's a write, invalidates the caching for the read. Again, this one is you're not gonna be able to detect this easily. You'll just see a lack of performance that you expect. So the cache counters or miscounters can help in this case. To do this, you just have to separate. You have to make sure that when you are working in similar memory spaces between multiple threads, that they're not too close, or that you're basically avoiding, you want to avoid cases like this, right? Anytime you've got threads that are going to be dealing with intensive memory operations, particularly one writing, one reading, or multiple readers, you need to separate those in memory so there's no worries about the cache getting invalidated by one thread and leading to the other ones not being able to do their work. Yep.
I don't understand what you mean by validate. Like, wouldn't it just get replaced and really that happen?
It would be nice, but what happens is, so you've got multiple processors, multiple cores, and each one has a cache. If they both read the same memory, it's loaded into their cache independently, and there are different ways to approach this, but the standard one is, it's called MISE? M-I-S-E? I don't remember. Basically, you'll have memory that's either invalid or it'll basically be valid or invalid. And the only thing that it doesn't, when a process modifies a cache line that's also shared, it doesn't do what you would expect, which is write to that value's cache. It just writes back to memory and sends and invalidates the other one. And so the only way they actually communicate values is through main memory or through the lower level caches. It's weird, it's sort of there are reasons in terms of complexity of hardware and just building up a protocol that makes sense. It's a lot easier to say, just invalidate it and go through memory. And so if any write will invalidate the cache line and then force it down to memory. And so if you're dealing with the same cache line, you can all read from it, that's fine. But if if writes are common, then reads will become slower. Or shared reads. Even though they're not reading and writing to exactly the same memory. Right? So the smart way, I'm going to talk about this later, the general advice is to parallelize at the top. right? Do parallelism at the high level, both programmatically and then also at, if you have two loops, parallelize the outer loop. I'll talk about why. In this case, the way to do this smarter is subdivide down to a certain level, and then once it fits in, L2 or L3 or something like that, parallelize at the bottom. Right? Once you get down to a small, that's one way to approach this. Is once you get down to a certain level, for example, we're going to at some point get to, an 8 by 8 multiplier or something like that. Subdivide down. When it's small enough, then parallelize. The problem is, partially, the whole idea behind cache oblivious was I don't know what the size of my caches are. I just know they behave in this way, right? They're increasing in size, and they're increasing in latency. To do this effectively, you can't do it, it's tricky you can't just do this cache obliviously with multiple threads, because you have to know the right time to parallelize. The optimal time is as soon as they're not going to poison each other's cache, right? So you subdivide until it fits in cache, and then you start parallelizing. And then they're reusing each other's data, and it's very efficient. But then I need to know what size the cache is. So again, I've lost this obliviousness, right? I have to know what size cache I have. I don't actually know if there are good algorithms for matrix multiply for multiple threads. For that, it may actually be easier to, I don't know, I'd have to look at the literature. It's not trivial because, again, you want to have both efficient parallelism and cache obliviousness to keep the obliviousness is tricky. All right. The other, another parallel or problem with parallelism is that scheduling overhead quickly can dominate. Not quickly, but, well, it can be quickly. And it will it's guaranteed, basically, to overwhelm parallel gains. Almost certainly, depending on your scheduler. Why? We have n threads. We're probably going to have to do work roughly proportional to n to schedule those threads. Or we'll have some suboptimal scheduler. And so this is sort of if this is number of processes, and we've got some amount of work to do, then we've got some fixed amount of work to do, then our execution time under sort of the optimal model goes like this, right? We have some number of, processors, K, not P, I don't know why. And the P is our workload. As K increases, the amount of time it takes to finish the work drops as 1 over K, right? And 1 over number of processors. If you take and add just in this, okay, I've got K minus 1, I have to schedule these other processors. And I have some C. Whatever C is, it's just positive. It's the amount of work I have to do to schedule these things per time step. Then I'll get this curve, right? At some point, at 10 or 20 or whatever, it'll improve down to here, but then after that, the scheduling overhead is higher than whatever gains I would get. And that's partly because, the difference between 50 processors and 30 processors is not very high, right? I've already subdivided my problem very small, so every little, if I've got just some small amount of extra work, it can quickly dominate the difference between these two. And if I'm increasing the amount of work I have to do for scheduling linearly, then the small change here is washed out by whatever cost increase I've got there. And this matches actual data in a lot of cases. Yes?
So the bad part is when that curvy curve intersects with a horizontal line that is like at the point D one.
You mean, when does this start to? It depends on C, and it depends on it depends on the size of P as well. So it varies.
But you want to draw a horizontal line at the point.
This is where you want to go to, right? And so if you can reduce your scheduling load, for example, if you do more amount of, if you can hand a large chunk of work to a thread and then just ignore it for a long time, then C can be you can push C down, right? Anything that you can do to reduce the amount of scheduling overhead. So the most common ways are do more work per thread We see this partly in the CUDA stuff, right? Where one of the common ways to improve performance is to do more work per thread. This is partially scheduling, this is partially just things wrapped around, index calculations, but it falls into the same bucket, right? Setting up and tearing down the threads. So all of that is pushing C down, right? Making C smaller so that it starts to approach this more. But eventually this will always happen. There's nothing you can do about this, right? Except for those tricks like pushing C down, right? This will happen. There's no avoiding it. But if you can push it up here where you have way more, if you push it up to 50 processes, you don't have that many processors anyway, usually, unless you're in extreme cases. But if you can put it down to around here through whatever mechanisms, then as long as your number of processes is as many as your what you actually have physically, you're fine. Okay? The GPUs, this is not the case, right? This is the case. It's just they have thousands of processors, but the scheduling overhead is very low because you don't have any sort of scheduling, right? You divide it up into blocks, especially the static scheduler from OpenMP. You take your problem of whatever size it is, divide it up into blocks, and run those in some order, and you have no control over what that is. In the multiprocessing world, or multi-core world, where you've got processes that interact or go to sleep while one reads from memory, the other one does something else, this becomes more of a problem. There's also, in the synchronization overhead problem, there's the slowest subtask is going to be is going to often limit your performance. This is something else to look for. This is particularly easy if you've got some sort of varying computational load. If you've got some sort of fork join or you've got a barrier where they need to communicate, you'll increase your number of threads or processes, and it won't matter, right? You'll get a much lower performance increase because the longest thread is going to be the limiter. So this one, you just have to figure out how to balance your work beforehand, but it's also something else to look out for. Very common problem. If you're into proofs of correctness, which can be useful, particularly writing new algorithms, parallelism is not going to be your friend, right? Induction, loop invariance, case reduction, all of these are easy in serial, very painful in parallel, unless you simplify your programming model to be something like, a queue of work, or you've got enough state with each task that you can always lead. You break it up into little serial pieces and do that on each little subtask, but then your overhead for keeping around that state is much larger. And you also have other problems that then can appear that are hard to prove away, deadlock, priority inversion, things like this. We haven't talked too much about this, so that's more an algorithms class, but it's something to be aware of. So, for example, I don't know who's done a loop invariant here. Loop invariants are basically you make some statement about the state of the world and consistency at the beginning of the loop. You show that through the entire loop, at the end of the loop, it's in the same sort of consistent state. You're temporarily allowed to break it. And then if you do that, and then you also make some statement about I'm moving towards an end condition, I'm always getting closer, then your loop will always terminate with the invariant in place and will always terminate as long as you make progress towards this end. So the usual thing is, I assert some invariant. It's true at the beginning, and it'll be true right at the end when I leave. I can temporarily break it and then fix it while I do some sort of work. It can be quite useful, breaking down complex problems into this sort of form. The problem is that this ends as a sort of critical section, right, where the invariant is temporarily broken. And if some other thread comes in there, you've got your invariant is not true and they're not able to communicate, or they're not able to, if one of them reads the invalid state temporarily, it's not going to work. So you need to protect this with some sort of lock or be aware of what it might read. and it makes it much more complicated. Many of you have hit, this is not just a pitfall, it's just dealing with pitfalls. Debugging parallel programs is difficult, it just is. There are no good tools for this. There are limited tools for this. Some of them record the entire state of the program every time anything changes. You can set up breakpoints in your favorite debugger or print out state changes, compare them to your expectations. Even better, make your expectations explicit with asserts. I think that this is true here. As you're going through the code, wherever threads might interact. Check the serial version. Run it with, just make sure that your algorithm works. Go through it, figure out what the assertions are that are involved in your serial version. Translate or move those to the parallel version as well, and then check it with just one thread. Right? Often, in the work to parallelize an algorithm, you introduce bugs that are present in the single-threaded version running on the same code. So comparing those two will often help flush out a lot of bugs. All right, some rules of thumb for avoiding these. Parallelize out-or loops. This avoids the scheduler overhead in particular. If you've got nested loops and you parallelize the inner loop, then you're creating a bunch of threads or doing a bunch of threads at the lowest level, and each time that C in the scheduling overhead increases. So try to parallelize over outer loops. Again, talking about the cache oblivious algorithms, that obviously doesn't work, right? Then you've got cache problems. Balance the work so that your slowest subtask finishes at about the same time as your fastest subtask. If possible, make them all do exactly the same amount of work. It's generally, if you can, use atomics instead of locks. The overhead is about the same, but the atomics code is much simpler. You don't have to worry as much about things like deadlock or anything like that. And along with that, avoid nesting critical regions when you are using locks. I'll go through an example for those. Part of this is to use local memory when possible. If you can get a subproblem into local memory and operate there, then you don't have any sort of interaction with other threads at all. Right? If each thread is operating on its local memory. You still have to worry about cache or performance, but you don't have to worry about as many bugs. So if you can snapshot a piece of the large problem, do a bunch of operations, and then write it back, this is often much cleaner and much more bug-free approach. I'll get to that. I'll get to nesting critical regions in a second. As we've talked about, certainly embarrassingly parallel are obviously candidates. Also, anything that you can phrase as a pipeline. I'll talk about this. How to parallelize those efficiently. So for the nesting critical regions, we saw some of this in homework 2. Right, we have this simple example of transferring bank balances or something like that, where we've got an array of values, a source and destination and amount, and possibly some locks available to us. All right, we can't do it this way because there are no locks. We have a critical region where certain values are being read and written to, and so this will, if you try to run this with multiple threads, it'll misbehave. Right, in this region in particular, where you could have multiple readers, writers to the same memory. So the nesting critical regions is, if we're going to do the lock, we're going to lock both accounts at once. Then you get all this stuff, well, when you nest critical regions, then you have multiple locks, right? You have a critical region, you have a critical region within there. You have to lock the outer one and the inner one. If those critical regions depend on particular values like this, where we're locking the source and the destination, then you get all this complicated logic of, lock this, not that, lock in this order, right? And then we get into the critical section. And several people, I think, hit problems with this, right? A bunch of people hit deadlock when they were doing homework 2 because they were locking in some different order. So to avoid the nesting, you can do something like this, right? You just lock the source, do all the work that you're going to do with source, and then unlock it, and then enter a critical region around dest. All right, so temporarily, it's out of, so again, this gets into the, loop invariant, right? The invariant here is there's always the same amount of money in all the accounts. Right, so temporarily right here, we've taken money out of the source, but we haven't put it in dest, and so there might have to be logic here to make sure the money doesn't just end up with the bank. But you do the same thing, right? You lock one section, pull the money out. Very few people did this in whichever homework it was. I think only one or two. It was surprising. Many people said, okay, I'm gonna lock both. So that's the default thing. But there was nothing that required that, and this is much easier. There's no worry about deadlock here. You only ever hold one lock. Right, so you have the critical region around source, critical region around dest. And then that allows you to rewrite it in a higher level, often, if you're using Python, but most languages, where you just do this, okay, I'll grab the lock and I'll do this block of code, and it handles all of the, okay, acquire, release. If I exit because of an assertion failure or something like that, it'll unlock as it goes out. Like when it returns here, it'll unlock on its way out. So that makes things easier in a lot of ways anyway. If they're not nested, you can use some higher level tools, right? We're using in this case, the context manager in Python. But then instead of locks, the code can be even easier and possibly more performant if you use atomics, right? So we're just gonna speculatively decrement the source account and then check if we actually had enough, right? Most of the atomic operators return the old value. So if the old value wasn't enough, then we'll put it back and then we'll just go on our way. Otherwise, we can do this. And so no locks are needed at all. The code's a little less clear because we do this take out money, and then if we took out too much, put it back. But in a lot of cases, this can be more performant and easier to debug. Because also, in this case, you're not worried about locks and whether or not or state that's there. You're explicitly saying, I'm gonna take money out and then check if I actually had enough. So you expect the value sometimes to be less than 0. And so it's not a surprise, and your code is more likely to deal with it correctly just because you already have this in your head. So the old value will always be, so the atomic, one of them will always decrement and get its old value first. And then the next one will decrement again and get the new old value, right? Yeah. So it's possible that you could do a large withdrawal and then a small withdrawal, and they'll both fail when the small withdrawal should have. But this is unlikely, and you're gonna have to deal with overdraws anyway. Right? This would be a temporary failure. You could, wrap it in something that says, okay, keep trying. But if you've already overdrawn your account, you don't necessarily expect it to work to overdraw it by less immediately. Does that answer your question? Okay. But the old value is also atomic. All right. And finally, pipeline parallelism. If you've got some large number of tasks which are embarrassingly parallel, and you've got some slow step, but the rest are fairly fast, right? You might do this, right? This is embarrassingly parallel. Okay, I'll just run it in a bunch of jobs. But if this is my slow step, I've duplicated each of these as well, right? This one might be slow, but this one might use a lot of memory. I'm basically using up 4 times as much resources, when really I'm only trying to fix this part. So in that case, it's usually just a lot easier to do this. Right? You've got low communication overhead here. This can just be a queue and another outgoing queue. This is slow, so it's not like it's gonna be creating a lot of data. And in this case, even if these use a lot of resources, I'm not duplicating them, so I'm not overloading my system needlessly. All right, so it's a more general form of the embarrassingly parallel. Which parts actually need to be in parallel? All right, parallelize over only the parts that you need to, and be wary of creating multiple processes or multiple ways of approaching multiple workers doing work that could be done in serial, but involve other resources being taken, right? The other thing I'm gonna increase here is my scheduling overhead, right? Especially if these are independent processes, or each of these is a sub program. Now I've got much more running on my system as compared to something like this, where I might just have 4 processes handing data off to each other, and one of them running multi-threaded, and that's the only one I need to speed up. So this one is just also profile with whatever means you have the performance of your algorithm to figure out what you do need to speed up. All right, that's the end of sort of things that can go wrong and how to avoid them in general terms. A lot of this you've already hopefully picked up along the way, possibly through painful knowledge acquisition. So next time, basically final lecture is on Wednesday. It'll be wrap up and course review. If there are any nagging questions, I can answer them then. If there are any questions about this, let me know. Keep up to date with your TFs on your final projects. You know, it's probably good to drop them a line before your next meeting. Just let them know your state, what your goals are for the next week, so that they can be ready to talk to you about that at your meetings. All right, thank you. See you Wednesday.